Hello, everyone. My name is Yungang Bao from ICT, Chinese Academy of Sciences. Very glad to introduce our recent work about the high-performance RISC-V processor. This is an open source project called Xiangshan. And today I will talk about two parts of Xiangshan. One is how we build Xiangshan and who is building Xiangshan. So first, I think I'd like to advocate that we are entering the era of open source chip. So this is actually inspired by the open source software ecosystem, so which has been developed for 4 decades. So with the support of open source software, so we can lower the barrier of innovation. For example, today, if we want to develop an app, a smartphone app, we can leverage many open source components, such as like Linux, like Apache, MySQL, or PHP. And with those open source components, probably 90% lines of code can be free accessed. And then we can only need to program like 30% and less than 10% lines of codes to customize our app application design. So in this way, probably we can develop an app by like 3 to 5 engineers with just like 3 to 5 months. So this is very agile and fast. So with the open source software, so internet startups has been benefit a lot from open source software. For example, if we take a look at the startup, how they raise funding, we can see that most startups only need like $500,000 to finish their proof of concept. This is called like seed round funding raise. And then for the round A funding, usually those startups need to raise like $3 million to complete a working prototype, and then raise the next round B, about like $20 million to get a customer engagement. This is a very typical steps of the growth of internet companies, internet startups. But if we compare with the chip startups, so usually we need to raise more than like $20 million to get the working prototype down. So this is a very high barrier for chip industry, and it is not. I don't think this is healthy for industry to grow up and to grow bigger. So our goal, or we envision that in the future, we can have an open source chip ecosystem, just like the open source software ecosystem, that can lower the barrier of chip development by saving time to market and the cost of like IPs, EDA tools, and some other facilities and engineers. So with this, in this ecosystem, for example, if we want to build a chip, a system on chip, and we hope that we can leverage 90% of lines of codes or IP modules to develop the SoC chip, and we only needed to customize, to finish less than 10% of customized codes. So this is our goal, and we hope in the future we can build up, we can have such an open source chip ecosystem. In particular, we further divide the open source chip into 3 levels. The following chart, the flow is a typical processor design flow. First, we need an instruction set specification, and then we do microarchitecture design to get a document, and then we do encoding and engineering to get the RTL codes, and finally we use the EDA tools to generate a layout, for example, like the GDS2 layout, and then send the layout to Foundry. This is a typical chip design flow. And if we look at this design flow from the open source perspective, then we can divide it into 3 levels. First is if the instruction set is open or not. This is we call it level 1. And for level 2, we say that if the design or implementation is free or closed. If free, which means we can freely access the documents and RTL codes. For level 3, we say that if the framework or the design tools are free or closed. If free, if a project can achieve level 3, which means it should open the framework and the tool and such infrastructures. So this is the 3 levels of open source chip. Currently, I don't think there is any open source chip project that can achieve level 3, but this is our goal. We are working towards level 3. So Xiangshan is the project towards level 3. So we launched the Xiangshan project 3 years ago in 2019. Actually, we started coding in 2020. And next, I will briefly introduce Xiangshan. So the first question is why we want to build an open source high performance RISC-V processors. So in particular, we first need to answer the question why we choose RISC-V. This is because RISC-V is an open and free ISA. Without open ISAs, it is impossible to get an open source design and implementation. So just like this table, so there are 3 categories for both specification and designs. For example, for specification, if the specification is closed, then it is impossible for us to get open and free designs. Similarly, if the specification is we need a license to get the instruction specification, it is also impossible for us to design open to design free and open processors. Only we have the free and open spec that we can do open and free designs. So this is why we choose RISC-V. And next is why we want to build a high performance RISC-V core. This is because we found that currently most RISC-V processors only are for IoT or for AI, like AI applications. And most RISC-Vs are for embedded environment. But both academia and industry community need high performance RISC-V processors. For example, like the ARM Cortex-A76. And this is a very typical high performance CPU core. And actually the license fee is quite is quite amount and it's not affordable for many startups. So if we can provide open source RISC-V processor that is compatible with the ARM Cortex-A76, then many companies, especially for those startups, they can gain a lot of benefits and to release their innovations potential. And the next question is why open source? Actually, we as a big fan of Linux, actually, I have learned and also benefit from a lot from Linux over the past 2 decades. I think Linux is an open and innovation platform for both industry and the research community. But there's no such platform for hardware. So we want to, I think it is appealing to see if there is a open and innovative hardware platform, just like the hardware version of Linux. So this is also our kind of religion for open source fans. So we want to build such an open source platform for hardware, especially for CPU. Then we come up with the idea that we want to build a leading platform with agile development flow and tools. So that is our motivation to build the Xiangshan to launch the Xiangshan project. So Xiangshan is the high performance processor. We have already finished 2 generations of Xiangshan. The first generation called Yanxihu, which is 64-bit RISC-V, single core superscalar out of order CPU, and it was taped out with 28 nanometer technology and can achieve 1.3 gigahertz. And the spec CPU performance is about like 7 points at 1 gigahertz. And so if we take a look at what is the position of the first generation, the Yanxihu, among other processors, for example, like other RISC-V, Sci-Fi P550, and like the ARM Cortex-A76, and so forth. And the Yanxihu is just between the Alibaba's Xuantie C910 and the Sci-Fi P550. Then we have built the second generation NANHU, and the performance is actually triple of triple of the Yanxihu, the first generation, and it can achieve about like 20 points at 2 gigahertz, and it will be taped out with 14 nanometer technology. And then if we look at its position of the other among other processors, it's just between, or it's almost achieve the Cortex A76 at the same frequency. And now we are working on the third generation, the Kunminghu, and this time we are not alone. We have close collaboration with industry partners, and they have given a lot of support to build the third generation, the Kunminghu. And the performance, the ATPATE, we accepted that the performance can achieve the 15 points at 1 gigahertz. So it's almost it's comparable with the ARM Cortex X1. So this is the roadmap of the Xiangshan projects. Next, I just give some details of the first 2 generations. The first generation is the Yanxihu. This is a lake in Beijing, and the chip was taped out 2 years ago, and last year, and it is everything. This processor is 11 stage and 6 wide decoder and rename, and there are some parameters of the microarchitecture. And the real chip was back in this year, this January, and we have on this associated the CPU, the flash, and SD card, and Ethernet, and the DRAM. And currently, it can run DAB operating system with SD card and Ethernet. And the performance is, if we use spec CPU 2006 as the benchmark, and the performance is 7 points at 1 gigahertz. Here is the performance, and here are some applications running on the Xiangshan chip. Then we have finished, we have completed the RTL codes of the second generation NANHU. NANHU actually is a name, a lake in the Jiaxing, Zhejiang province in China. The target is 2 gigahertz at a 14 nanometer technologies. And the spec CPU, the performance of spec CPU 2006 is 20 points, 20 marks. And we have made 4 major changes over the first generation. For example, we introduced a new front-end design, we improved the back-end design, and we have redesigned the L2 cache. And also for the NANHU, we will tape out with a dual core, with dual cores. This is the estimated performance of NANHU. It can achieve, it also for spec CPU, the performance is almost around 20 points at 2 gigahertz. So this is the general information of the Xiangshan project. Next, I will introduce how we build Xiangshan. So actually, we have been using Chisel for years, and then we decided to use a Chisel-based Agile design for the Xiangshan, which means that we use Chisel to generate the Verilog codes, and then use the traditional EDA tool flow to generate the layout, and finally send that to the foundry. So this is the kind of different from traditional chip design flow. But why we choose Chisel? Because we have confidence with Chisel, since we did some experiments to apple compare with Chisel and Verilog. This for example, here we did an experiments by assigning a same task to 2 guys. One is a 5-year engineer and another is a senior student. And the same task is to design an L2 cache for RISC-V rocket chip core. And they needed to design the L2 cache and then integrate the cache into rocket chip CPU core. And here is the result. For the 5-year engineer, he took about like 6 weeks and he programmed like 1,700 lines of codes, and finally integrated the cache into the rocket chip, but it was unable to boot Linux. But for the undergraduate, he used Chisel, and he took only 3 days to finish the design, which is only 350 lines of code. And the design can boot Linux on multi-core RISC-V, even support the NIC with DMA mode. So for this experiment, we can see that Chisel is more productive than Verilog. For that task, for the specific task, the productivity improvements is almost like 14 times with only 1/5 lines of code. And next is the task is we have assigned a task 2 to a junior student who never knew Chisel. The task is to translate the Verilog code written by the engineer, the 5-year engineer, into Chisel, and then evaluate the translated code on the FPGA. So here is the result. The first line, the first column is the performance, the PPA of the Verilog code written by the engineer, and the third column is direct translation from the Verilog code into Chisel, and then we can see that the frequency is already better than the Verilog version, and only the LAT logic is slightly more than the Verilog code. And with the help of a PhD student, then the junior student even improve the Chisel codes by quite a lot. And for example, for performance, the frequency improved by like 13%, and the LAT logic is reduced by like 54%. So in this, for this experiments, we get a conclusion that actually Chisel can achieve better PPA than Verilog if we know well about Chisel. And so that is give us a lot of confidence that Chisel actually is quite like competitive with traditional hardware languages. So then we decided to use Chisel to build a high performance RISC-V code. But we encounter many challenges of chip design. Since it is already programming is very fast and agile, but verification becomes a big challenge. Traditionally, usually we have feature requests and written and programmed by Verilog, and then we get the silicon-proof IPs. And here is the flow is based on the Verilog code. And we do like a simulation, and then we debugging, and finally we modify the Verilog code and to get a loop, a verification loop. But when we use Chisel, and the feature is written or programmed by the Chisel language, but the verification flow is still based on the Verilog. So this is broken between the traditional Verilog-based flow and the new hardware language. So next we have to done a lot of work to fill the gap, to build and close an agile loop. So next I will introduce our work how to bridge the gap between the agile design and the traditional verification. Here we have built a bunch of tools for agile verification. Based on existing EDL tools, we have built like more than 10 tools to form an agile verification flow. In particular, we have to finish, we have to complete two functionality. One is we needed to perform the agile functional verification, which means we need to verify if the design or the modification to the Chisel codes is correct or not. So here is a cycle of the loop of the agile functional verification, and we have the red box or self-built tools. If we look at the conventional verification, which verify the consistency of output of the design, the DOT, the design auto test, and the REF, which is reference model. So in this case, usually the reference model, which is the REF, requires implementation details. But this way, this traditional verification suffers from the traditional, the agile design, especially like a chisel-based agile design. Why? Because for chisel-based agile design, we write chisel codes and then generate Verilog codes, which means it's very easy for us to generate many different Verilog codes. And for each generated version, we have to build a specific REF, the reference model, which actually brings a significant overhead to the verification engineers. That is why when we talked to those engineers about the agile design, for verification engineer, they are all kind of refused to accept agile design. So, and there are also raised some new challenges. For example, sometimes with the same specification, there can be multiple diverse legal designs. For example, if Linux allocate the valid page table entry and then lazily execute memory barrier instruction, in this case, we will see two legal execution paths. For the left, this is very traditional normal execution path. It's PTE allocation by the operating system. This is a store instruction. And but for the right path, the store instruction, the data was buffered in the store queue, and then laterly, but the data was not written back to cache hierarchy. Then next, if the CPU execute a load instruction to access a page, and for the left path, it's legal, and the data is updated to the CPU pipeline. But for the right path, since the new page table is not updated to the cache, then a TLB miss occur, and then the CPU has to deal with the TLB miss and even the page fault exception. And after exception, then so in this case, there are a mismatch between the two passes, and for the right pass, and then we have to execute the load instructions. So these two passes as both are legal, but actually this will raise a lot of implementation of reference model, the overhead of a reference model. So how to deal with this case, especially we are easily to generate those the Verilog code. So actually we borrow the idea from software programming methodology. Here we propose the differential rule-based agile verification. Actually, we can think about what is correctness and what is the golden reference model. So we have the insights that specification actually is eventually the eventually golden reference model. So once the design matches a specific specification, then we can say the design is correct. So for a given specification, there can be diverse implementation. But the next question is how to describe the specification and how to abstract diverse implementation into one specification. Actually, there are different ways. For example, we can use natural language to describe a specification. This is very flexible and with a very high level abstraction, but it's not accurate, not precise. Now we can also use like a system Verilog to to describe a specification. But in this case, we have to there are a lot of engineering work to describe details, implementation details. And we can also use like some formal model, like cell model, but it's still, we need many details. And our approach is using rules. Just like the case, for example, we can use 2 rules. Here, for time limitation, I will not give them more details. Just use rules. Then we can use rules to abstract different behaviors or different implementation and designs of the CPU design. Here is the framework of the differential-based agile verification. We have a probe which is inserted into the design code, and then we have the rule check, which is plugged on the reference model, and they can do compare and do checking if the design is follow the rules. This is the first part, and the second part is how to perform the agile performance verification, which means once we modify a design, we need to know if the design is faster, if this modification get a better performance or poor performance, which means faster or slower. Usually there are different ways to do performance modeling. And for example, we can use emulate, but which is very expensive, usually millions of dollars. And we can also use like FPGA, that is faster, but the scalability is an issue. And also it is not able to emulate a very large scale processor design. So software-based simulation, for example, like a Verilog, like VCS is able to simulate the whole RTL design, but it's very, very slow. So we want to figure out a way to speed up the software-based RTL design. Our approach actually is with checkpoint and sampling, and it can we can use for example, we can get the performance of spec CPU on Xiangshan with just several hours, less than like 6 hours, with enough servers. So this is very faster. This is our approach. So in particular, there are 4 steps. For the first step is to chop the whole program execution into multiple slides. And then for the second step, we will use a machine learning algorithm to choose the representative slides. And for the third step, we run the slides on the RTL emulators. And finally, we use some algorithm to reconstruct the performance to combine those together. And here is the performance evaluation result. So we on this chart, we can see that the performance of RTL simulation is almost the same as the FPGA emulation, and also almost the same as the real chip. So which means that our approach is convincing. So put it all together, we have built an agile development infrastructure for Xiangshan. Here is the flow, and those are tools. We have the self-built tools for the agile development flow. And we want to emphasize that both Xiangshan and the infrastructure we call Mingjie are open sourced. So this is just the iceberg. We consider that the upwater part is the Xiangshan, and the underwater part is the Mingjie framework. Both are open sourced. And so everyone can access Xiangshan on the GitHub. It has already gained more than like 3,000 stars and about like 380 forks. And our work is also published on Micro this year. If you want to know more details, please please read our paper. So actually, Xiangshan is towards level 3, but I have to admit that we still unable to achieve level 3 yet, because already although we have open sourced some self-built tools, we still need to use a lot of commercial EDA tools from Synopsys, Cadence, or Graphics Mentor. Okay, that is my talk. Thank you very much.